Hi everyone, today we're going to look at how to analyze a doubly reinforced section as per the Eurocode 2. Now starting this by defining a doubly reinforced section. If you look at this figure, you see that we don't only have one layer of reinforcement, but we have two layers, at the bottom and at the top. We name the reinforcement at the top as compression reinforcement, and it has this notation A sub S prime. So whenever you see the prime sign, then you should relate this to compression reinforcement. The very significant reason that we go for a doubly reinforced section is that we don't have enough internal moment of resistance to resist the applied moment or the design moment, and that we do so by checking the K value. If you get a number equal to or greater than 0.167, then you must go ahead and provide the compression reinforcement. So this is one of the solutions. And another reason that we go for doubly reinforced sections is that the architectural requirements. Suppose that I don't want my occupants to observe the beams inside a building. Suppose that is the case, then I do restrict. I can do this by restricting the depth of my beam, but by doing so I should also know that I'm also risking the internal moment of resistance. The section will not have the same moment of resistance if I'm going to reduce the depth. So I can reduce the depth, yes, but in that case I'll have to provide the compression reinforcement. Now for most of the cases, if not all the time, you'll see just take any cross section through any beam. You must see the compression reinforcement, and if they are not there to provide any extra moment of resistance, then they are there to act as hangers. What you see in blue is what is called the shear reinforcement or links, and they must be there most of the time in beams. Must be there because shear reinforcement or shear force in a beam is quite high when compared to other structural elements, so that it wouldn't really be possible to provide the shear links when we don't have compression reinforcement. Now let's just go ahead and derive the equations necessary for the calculating area, the area of reinforcement at the top and at the bottom. We're gonna need the stress distribution diagram, and that from the single reinforced section we know that it's simply going to be like this. Here we have an extra or an additional force which is at the top. Now we have the steel there, and it has to have a resultant compressive force acted by the steel at the top. We name it as F sub SC. If you look at this cross section, you'll see that the reinforcement at the top has an effective depth. It is given as D prime, and as usual we have the effective depth of the tension reinforcement, and from equilibrium we know that the forces at the top must be equal to the forces at the bottom. We can just go ahead and define something very important. See, whenever we are putting the compression reinforcement, we must select some terms. We have the Z or the leverage or the level arm, and there's also the S or the depth of the stress block. There's also the depth of the neutral axis. Whenever we are dealing with doubly reinforced section, then we need, it is a must that we go for a balanced section. So whenever we come across these three terms, then we need to take them as per the limit. So for the depth of the neutral axis, it is just 0.45D. What that means is that we are also ensuring a ductile mode of failure. So whenever we come across these three terms, we're gonna just take them in terms of D. Now, as we said, the forces at the top must be equal to the forces at the bottom, and that we make a very important assumption here. Whenever we are talking about the stress in a steel, then we take it as the yield stress, and in that case we just multiply it, the characteristic yield strength of steel, we just multiply it by this partial factor of safety, which is 0.87 as per the Eurocode 2. Now we don't have only one rebar, but we have two layers of. So what we are assuming here is that both the rebars have yielded, and that the stress in that steel gonna have this value 0.87 F sub YK. We're building this assumption, and we must prove it as well. We're gonna do that later on with the strain diagram. So we just move ahead, and remember, whenever we come across S or Z or X, we just put them in terms of D. That's what we did there, and instead of writing S, we are writing 0.360. So I'm gonna name this equation n, because we need this equation to derive both the area of compression reinforcement and the tension reinforcement as well. What I need actually here is that I need to, well, get rid of the unknowns. I can do so by eliminating the area of reinforcement at the bottom, or the force at the bottom, and we can do so by taking the moment at that point. The moment will be 0, of course. At the top, well, we have the resultant compressive force of the steel multiplied by the level arm, and we have the resultant steel compressive force. We just multiply it by d minus d prime, and that's the level arm for that force. So we carry on the calculation. We take z as per the limit. Just rearrange that equation, and now I think we are ready to get the a prime. This is how we find the compression reinforcement in a doubly reinforced section. Now I'm going back to that n equation, and well, if the forces are equal, then the moments also should be equal, and that, well, just by multiplying both sides by 0.82d and then rearrange the equation, I'm gonna end up having the area of tension reinforcement. What we can tell here is that first of all, we have to determine the area of compression reinforcement, and then we will just be able to find out the area of tension reinforcement. So, well, we can go ahead and put or determine the area of reinforcement in terms of K. So instead of writing in terms of moment, manipulate with the equations, and then we can just determine the area of reinforcement for both compression and tension in terms of K. Now, I said before that there's a very important assumption, and that we are assuming not only the compression reinforcement but tension reinforcement as well. They both have yielded. We need to ensure this by ensuring some of the ratios. Now we have the d prime over d. This must be less than 0.171, or the d prime over x must be less than 0.38. Based on that, our area of reinforcement, either at the top or at the bottom, is valid. So we can go ahead and take that equation of area of reinforcement and apply it, just apply it, and then get the value. That's totally valid. Someone might ask, how did you come up with this ratio? Now, simply, we know that the steel has almost the same behavior in compression as well as in tension. At the top, it's going to have it's going to be in compression, of course. Whenever I say that the steel has yielded, then what I'm referring to from the idealized strain stress diagram is that the area with a dotted rectangular. Only in that case, I can say that the stress in a steel is equal to the yield strength of that steel, and I just multiply it by 0.87. I can also find the strain, epsilon sub SC, and it is just from the slope. And from the slope, I can tell that the strain is equal to the stress over the elastic modulus. Elastic modulus of steel is going to be the same always for all the grades. I can just go ahead and substitute the modulus of elasticity, and then what I get here is 0.00217. This is my strain, and this is the strain for the grade 500. If my section has strain something larger than 0.00217, then I can go ahead and say that my steel stress is equal to 0.87 FYK. So what you see here is the strain diagram of a doubly reinforced section, and by having this similar triangles, I can just, well, I have this proportion, I can just determine a ratio. Now the epsilon SC over the maximum strain allowed by the Euro code for the concrete is just 0.0035, and that is equal to x minus d prime over x. If I go ahead and rearrange the equation, and then I put that limit for my epsilon sub SC, then I'm gonna end up having the d prime over x should be less than 0.38. And by having this figure, I must also, well, if I just instead of writing the d, I can just take the balanced depth of the neutral axis and then substitute it there to have another ratio, which is d prime over x. Now this is my ratio. So if I'm gonna check my section and I put this ratio and I get it less than the numbers showing, then I am fine. It should be fine. My assumption is valid, and that the steel in my section has yielded, the compression steel. Now, what if my steel hasn't yet yielded? Then that means it is within this dotted blue rectangular. So it is within the slope. And that means it hasn't yet reached its yield strength. So I cannot say that the stress in that steel, in compression steel, is equal to 0.87 times 500. That's for the grade of 500. And that my assumption up there for the compressive stress is not valid. That means I'm gonna need to work out the stress again, and from the slope I can say, well, simply the stress is equal to modulus of elasticity of steel times epsilon of the steel at the compression zone. I already have the elastic modulus, but there is one unknown, which is the strain. Now the strain from the strain diagram on the right hand side is equal to 0.0035 times x minus d prime all over x. So this is the epsilon, but I cannot determine the strain. This is because I don't have the depth of the neutral axis. And in order to find the depth of the neutral axis, we need to go back to this equilibrium equation. And that instead of writing 0.87 fyk, I'm just writing the entire term on the right hand side, the f sub sc, which is the entire term on the right hand side. And then that if I break the s, I will be ending up having not only 1x but 2, so I'm gonna end up having a quadratic equation. And from that I can just work out the depth of the neutral axis and then get back to the stress, find the stress, and then I should be fine. Now this might sound awful, but well, it's not that difficult, and hopefully we are not going to see any of this. Indeed, we're gonna have one example where the compression steel and the yield steel have yielded. Alright, we can just summarize this. So whenever we have this ratio for the compression reinforcement showing there, we can say the yielding of reinforcement is ensured and that the area of reinforcement is valid in that equation that we derived. There's also the yielding of tension reinforcement. So it is just basically the same thing. You do it with a strain diagram, and then you will end up having something like this. It is x over d should be less than 0.617. That will ensure the yielding of tension reinforcement. So if I'm ensuring all of this, then I can say that the stress in the steel, either the compression steel or the tension steel, is equal to 0.87 times the characteristic yield strength of that grade I'm using. And that I can just go ahead and find the area of reinforcement from the equations that we derived. There's also one important thing that remember, all the equations for both tension and compression reinforcement, we derived them based on balanced section, and that I don't have to check whether the section will have a ductile mode of failure or not, is already ensured. Now we should be fine and go ahead and do the example 1. Now here we have to determine the area of reinforcement for the simply supported beam with a rectangular section, and we have the characteristic strength of steel as 500 megapascal and 30 megapascal for as the characteristic strength of the concrete. What we can see here is that I'm having this simply supported beam with a rectangular section, and I'm applying the ultimate UDL. That means I don't have to worry about any of these dead and live loads, and that I only take this ultimate UDL and put it there to work out the design moment. So that means we don't have to calculate the dead load and the live load and then put them into this load combination. It is already given, and that is a concern of the well, it is a concern of analysis, but in the design we do that. We do calculate the dead load and the live load and then put them into one load combination, and then finally we have the ultimate applied load. Now it is given there, it is given as 50 kilonewton per meter. There is also this rectangular section, it is given, and that we have to make sure that we really don't need all the dimensions, and I really don't know whether this section should be only singly reinforced or doubly reinforced. Well, I have to determine that with the value of k. So well, essentially I need the breadth and the depth. So I'm putting this tension area of reinforcement. That does not mean that I'm going for this 2 rebars. It is just there to show the effective depth of this beam. Now, well, by starting simply, I'm having a simply supported beam, so the moment is WL square over 8, and of everything that I need, I determine the moment. It is 225 kilonewton meter. Now I just go ahead and determine the value of K. Remember, M is the moment applied, and then put the values there, and you get a K of 0.187. Obviously, this is more than the limit. If it's more than the limit, which is 0.167, so we must provide the compression reinforcement. So what does K tell me is that my section must be doubly reinforced. So I'm gonna add or modify my trial section so that I have 2 layers of reinforcement. I already have the same D, I already have the same breadth. I'm just gonna add this D prime. I'm gonna give it 50 millimeter. So before just going ahead and apply the area of reinforcement formula, I must ensure that my section or my steel, my compression steel, has yielded. There's also another check for the tension reinforcement, whether it yielded or not. What is giving there is just will allow me to check the compression reinforcement. I already have the D dash, I already have the D, and what you get is 0.125. So that means simply, well, this is less than what is required to ensure yielding of the compression reinforcement. And that tells me the compression reinforcement has yielded. So I'm fine, I just can apply the formula. Now remember, I haven't yet checked the tension reinforcement, but I'm gonna do that sooner once I have all the required terms. So well, I have the K. I can just represent the formula with K instead of moment. Well, I can just go ahead, plug in the numbers, and then here we go. We get the area of reinforcement required for the compression reinforcement, and then we get the area of reinforcement required for the tension zone. There's just the Z balance there, and as we said, the Z balance is always 0.82 times D for the doubly reinforced sections. We just put the values there, and we get the area of tension reinforcement. So I'm gonna go ahead and, well, I have this table. It shows the area of the bar size against the number of bars, and well, I already determined the area of reinforcement required below the neutral axis, and that I have it as 1,566, and I'm just picking up a value near to that. So I'm taking 161, so I'm taking 1610, and that gives me a new area of reinforcement. It is obviously larger than the one I calculated, so that means I'm going to use 2 rebars, each with 32 millimeter diameter. And for the compression reinforcement, well, I'm gonna choose pick up 2 rebars, each with 12 millimeter diameter. So my section gonna look something like this. Now remember, that does not mean that I just go ahead and put these rebars. There's also the detailing, there's also the design, but that right now is not our concern. We're gonna stick on the analysis only and how to find the area of reinforcement. So we just leave it there. So we said that the compression steel has yielded, but has the tension steel yielded or not? Let's check it out. Now there's this limit x over d, or this ratio, and it has to be less than 0.617 to ensure that the tension reinforcement has yielded. So I'm going back to the stress distribution diagram, and well, in equilibrium I have this. Well, first of all, I'm going to assume it to be yielded, and then from this equilibrium I need to find the S. So what is unknown there is the S, and by putting that on one side and other terms on another side, I can just determine the S. Now, well, if I determine the depth of the stress block, that means I can determine the neutral axis depth, which is simply x is equal to S over 0.8. And here we go. The value of the neutral axis is 177 millimeter. So I'm gonna check this ratio. So 177 divided by 400, the depth of my section, and that gives me a number less than the limit. So what I can say is that the tension steel has also yielded. So my assumption is valid. So can we just determine the moment of resistance of that doubly reinforced section? Well, we can do so, and well, Well, to do so, we have to take the moment. Now we have this equilibrium, and we have the forces at the top and the forces at the bottom. And it's either I take the right hand side or the left hand side and then just multiply it by z. I'm going to go for the right hand side and just multiply it by the level arm. Now for the z there, I'm going to just break it down into d minus s over 2. Now someone might say that why can't you just go for the z balance? Remember, here we don't have to take the z or the x or the s balance. We just take it from the diagram. We calculate it from there, and we only go for that balanced section when we are calculating the area of reinforcement. So simply put all what we have got there, and the area of reinforcement that you put is the new one. You don't put the old one. So my moment of resistance happens to be 232.7 kilonewton meter. It is very important to check it with the moment applied or the moment of design, and it's just 225. This is logic because I added up more area of reinforcement, and that means I'm gonna have more moment of resistance. So since my moment of resistance is bigger than the moment applied, then it is okay. My section will not fail under the applied moment.